Here is our flow chart. You have to realize that there are 4 types of alkyl halides: methyl, primary, secondary, and tertiary. Methyl can only go SN2 because it only has 1 carbon. If we had more than 1 carbon, like we do in the primary, remember, primary alkyl halides means that the carbon the halogen is attached to is directly attached to 1 other carbon. If we have a small base, we have substitution, nucleophilic, 2 things happen at the same time. Or if we have a big bulky base, remember there's only 1 big bulky base, we're going to get elimination, 2 things happen at the same time. Secondary, it's not the size of the base, now it's the strength of the base. It's one of these weak bases here, right? Then we're going to undergo substitution. If it's a strong base other than these 3, we're going to say we're going to get elimination. If it's a charged or neutral under tertiary, we got 2 things here. If it's charged, we have elimination. 2 things happen at the same time. Or if it's neutral, we got to ask ourselves, is the solution hot or cold? If it's a cold solution, then we're going to get primarily SN1. Substitution, nucleophilic, 1 thing happened. Or if it's hot, we're going to get E1, which is elimination, 1 thing happening at any one time. Here's our methyl halide. And what happens is a pair of electrons on the CH3O-. We're calling that anytime we have a group 1 element like sodium written next to the oxygen is negative. So the pair of electrons on the oxygen attacks the carbon and therefore kicking out our leaving group, which is Br-. The Br- hooks up with the Na+, so we get sodium bromide, NaBr, and we get an ether. Now, if we use a big bulky base, remember potassium terbutoxide is our big bulky base, then what happens here is instead of being able to get to the carbon to substitute, we pull off a proton instead. As the proton is pulled off, the double bond forms and Br- leaves. We get an alkene in all elimination reactions in this chapter. We also generate sodium bromide and terbutanol. If we run a weak nucleophile on a secondary, now this is secondary, why? Because the carbon where the halogen is attached is directly attached to 2 other carbons. So therefore, I-, let's go to our mechanism slide, comes in and we actually get inversion of the center. The H starts out pointing up, slightly back, but in the end it's pointing down. So on secondaries with weak bases, we get inversion of the center. Here's a typical example, and remember this right here should be Cn. Okay, so make sure you realize that. Here we have a strong base, so instead of getting substitution, we get elimination. 2 things happen at the same time. Pull the proton off, leaving group leaves. One thing we want to realize here, and that the H that gets pulled off has to be anti to my leaving group. Of course, over here, we notice we get a mixture of products. It says Zaitsev's rule says the product with the least number of hydrogens directly attached to the double bond should be your major product. So you notice the compound on the bottom has how many? 2 hydrogens attached, where the compound on the top, which is our major product, has only 1. Here is the elimination mechanism. Remember the difference between the reaction, which is just the starting material, arrow, reactant, and products, as opposed to pushing the electrons. Pushing the electrons is the mechanism, okay? We see a pair of electrons pummels into either of these 2 H's, which again are anti to my leaving group, giving us a mixture of 2 products. Now, the interesting thing is what happens when we use a big bulky base. Instead of getting our Zaitsev product, we're getting a Hofmann product instead. We're pulling the proton off the H of the CH3. We're pulling the proton off here, forming an external double bond to my ring. Okay, now the tertiaries. Anytime we're talking about tertiary, the leaving group must leave first. That's how it's depicted here. for the substitution at cold temperatures, we generate a sp2 hybridized carbocation. The nucleophile can come in from either side, giving us a mixture of two products. But under the hot, this thing, as the leaving group leaves, which happens first, then our neutral nucleophile will pull off one of three protons to give us a mixture of products again. Solvent effects. And remember, for SN1, you need a polar protic solvent. And for SN2, you need polar aprotic solvents.